In this video, I've brought 6 of the most interesting problems for you. After doing some thorough research, I picked these puzzles and designed each one in a way that helps sharpen your mind and improve your problem-solving skills. And just a quick disclaimer, the goal here isn't just to find the answer, but to enjoy the process of how we get there. I can assure you, following this series will help train your mind to see things from new angles. Alright, here's our first puzzle. Find the missing numbers. We have a grid of numbers with 3 of them missing, and the goal is to figure out what those numbers are. At this point, I'd encourage you to pause the video and see if you can work it out on your own. Okay, let's start. A good first instinct might be to check the sums of the rows, but as you'll see, there's no obvious connection or clear pattern if you try the usual methods. So instead of looking at the numbers individually, what if we look at them as pairs? 1 and 6, 2 and 0, 2 and 4, 2 and 8, and so on. And now you will start to notice something. Starting with the very first row, if we combine the pairs, we get the numbers 16, 20, 24, and 28. These are clearly multiples of 4. Interesting. Now let's check the next row. We've got 20, a missing number, 30, and 35. These look like they are multiples of 5. And the third row, 24, 30, 36, and 42. All multiples of 6. You've probably guessed it by now, the remaining rows must be following the pattern. Multiples of 7, 8, and 9. The rows with missing numbers are 5, 7, and 9. For the first missing number, since the second row seems to be a multiple of 5, and the number starts with a 2, the only multiple of 5 in the 20s is 25. So the first missing number has to be 5. For the second missing number, the numbers here are multiples of 7. We have a number that starts with a 4. The multiples of 7 in the 40s are 42 and 49. We can see 49 is already in this row, so our missing number must be a 2 to make 42. For the last missing one, which is in the 6th row, these numbers are all multiples of 9. We have a number that starts with a 6. The only multiple of 9 in the 60s is 63, so the last missing number is 3. That's it, we've solved the puzzle. The missing numbers were 5, 2, and 3. Here's our second puzzle, and this one's going to test your spatial thinking. We have a grid made of matchsticks, and your challenge is to remove exactly 3 matchsticks to leave exactly 3 squares. Take a moment to pause the video and give it a try yourself. When I first looked at this puzzle, my natural instinct was to focus on the top area. Maybe if I remove these 3 matchsticks here, if I take these away, then it will leave us with 4 squares, which is wrong. We need to try another approach. What if the key is in the middle section? And maybe I should remove these 2 matchsticks of the third square from the top, and this horizontal one on the left. Removing them leaves us with 2 squares and 1 rectangle, which is again wrong. Here's where we need to think differently and approach this more systematically. I'm going to remove this vertical matchstick of the second square from the top. We have 4 squares left. Now if I remove these 2 matchsticks of the last square, and there we have it. We've removed 3 matchsticks and we now have exactly 3 perfect squares remaining. We've solved the puzzle. Here's our third puzzle, and this one's all about spotting patterns in numbers. We have this triangular arrangement of numbers. The top row has 5 numbers, the middle row has 4, and the bottom row has 3. But there's one number missing. Problem statement says that the numbers in the second row are determined by the relationships of the numbers in the first row. Likewise, the numbers in the third row are determined by the relationships of the numbers in the second row. Take a moment to pause and see if you can crack the pattern. To make it easier, if we first find out the relationship between the first and second row, then we can eventually figure out the third row. Also, this triangular shape gives us a clue that each number in the second row is determined by 2 numbers from the first row, meaning we can break this down further, and just figuring out the relationship between these 3 numbers and making the equation valid will solve the puzzle. Let's see if trying some usual methods can work. Subtraction? Nope. Division? Nope. Maybe sum of square roots? Still no. Here, we need to think differently, and instead of applying operations on these numbers as a whole, think of them as individual digits. What if I add the digits of each number? 8 plus 9 equals 17. 5 plus 3 equals 8. Adding those results together gives us 25. I think we've cracked the puzzle. Before going to the conclusion, let's check if this pattern holds for the other numbers. Sum of 5 plus 3, which is 8, and 1 plus 7, which is 8 again, gives us 16. Similarly for the other numbers, the pattern is clear. For each pair of adjacent numbers in a row, we add their digits separately, then add those results together to get the number in the row below. Now we can apply this to find our missing number. We need 16 and 17 from the second row, and take the sum of 1 plus 6 and 1 plus 7, and it becomes 15. That is how we have solved the puzzle and found our missing number. Moving to our fourth puzzle, connect all the 16 dots. We have 16 dots arranged in a 4x4 grid with an X marker above the center. The problem statement says that without lifting your pencil from the paper, draw 6 straight lines that connect all of the 16 dots. To make things more of a challenge, the line pattern you create must begin at the X. I'd again encourage you to pause the video and see if you can figure it out on your own. The marker X at the top is more of a hint, rather than making it challenging, because it gives you a clue that you need to think and move outside the box, rather than staying within the boundaries of the dots. Because no matter how many times you try, you'd need way more than 6 lines to connect every single dot while staying inside this box. Okay, so we start from the X marker, just as required. We'll move left and extend the line beyond the bottom of the grid. By doing this, the second line can clearly touch all the points diagonally. The third and fourth lines go the other way and connect 4 dots. The fifth line goes diagonally again, and our sixth and final line completes the pattern. 6 straight lines starting from the X, connecting all 16 dots, and we never lifted our pencil. This puzzle is quite famous because it challenges one of our most basic assumptions. Moving to our fifth puzzle, and this one is about cracking codes. We have a table showing numbers and their corresponding code numbers, and then we have a missing number that should correspond to 485. The challenge is to figure out the pattern that transforms the original numbers into these code numbers, and then determine what that missing number should be. Pause the video and see if you can spot the relationship. Since we've made it this far, we know that usual methods probably won't work here either. I'm going to start with the first example, the number 589 and its code 125. Look at the individual digits carefully. What if we take the last digit from the number and the first digit from the code? 9 plus 1 equals 10. Interesting. Similarly, the sum of the second digits of both numbers equals 10. The sum of the first digit of the number and the last digit of the code also equals 10. Another way of saying this, if we take each digit of the number 589, starting from the last digit, and subtract it from 10, we get its corresponding code, which is 125. Let's verify this with the next two numbers. 724 should become 683. 10 minus 4 equals 6. 10 minus 2 equals 8. And 10 minus 7 equals 3. That gives us 683. Perfect. One more check with the third example, and as you can see, the pattern definitely works for this one too. Now I can solve for the missing number. We know the code is 485, so I need to work backwards. Take the first digit of the code and add it with the number to make it 10, which is 6. So the last digit of the original number is 6. Similarly, take the number 8, add it with 2 to make 10. Take the number 5, add it with 5 to make 10. This gives us 526 starting from last digit. So our missing number is 526. That was easy. The key was just to recognize that the sum of corresponding digits always equals 10. This puzzle shows us that sometimes patterns can be hidden in the simplest mathematical relationships. Here's our sixth and final puzzle. This one is also going to test your spatial thinking. We have a chalkboard with a simple equation written on it. 7 equals 1, written in Roman numerals. But of course, this equation is completely wrong. The challenge is to move just one single line to make this equation true. Just one line that can turn a false statement into a mathematically correct one. Take a moment to pause and think about this. If you keep manipulating the numbers within the Roman numerals, then no matter where you move the line, left or right, there's no way to make it true. So I'm going to highlight this line that we're going to relocate. Now look carefully. Instead of keeping this line as part of the Roman numeral 7, I'll move it and place it horizontally right above like this. And there we go. By moving that single line, we've transformed 7 into the square root of 1. And just like that, it turns into a true statement. Square root of 1 equals 1. Sometimes the most creative solutions come from changing our perspective entirely. I hope you found these puzzles helpful. Until next time, keep thinking outside the box.